I wanted to thank Kim again because we did 10 years worth of lectures before these started. That's history in the library. And she did the artwork and she did a whole bunch of other stuff. She was always there to help. She came up with good ideas. She was really professional, but she was a friend too. So I just wanted to thank her again and apologize again for forgetting to thank you on that first session. Okay, so thanks a lot, Kim. I really appreciate it.
Thank you guys
And
for doing this for the community.
Can I also say, everything that I've done here, you taught me how to do
Oh.
it. So everybody knows, she taught me how to do all of this. So thank you. She's a graphic artist and she's amazing.
Yeah, so, stuff like that I really appreciate. And also, couldn't have done it without Denise. I really couldn't. I mean, she's got the expertise. Absolutely could not do it. I'm not exaggerating. And she has been a huge help to me in everything that I've ever done. And I've been a little tense lately, and she has borne up really well. So thanks a lot for putting up with me in my agitated and crabby way as I tried to get all this under my belt.
Ah, you're
I'm
worth
old.
it. You're worth it,
It's her
darling.
birthday tomorrow.
Oh, no.
So, how about happy birthday to you? Happy birthday to you. Happy birthday, dear Denise. Happy birthday to you. Well,
Thank you so much.
the harmony wasn't a winner, but
That was really nice.
that was your fault. You didn't hold up your end. Anyway.
Who, me?
No. Okay, so anybody else that I should thank? Just anybody that keeps coming out. I really appreciate it. Yeah, this gives me a chance to talk about this stuff, and I'm really appreciative of that. So I put a few things on the board just to cover stuff we've already covered, and we're going to be covering a lot of this we haven't covered yet. But if it's up there, and you can see what it is, when I talk about it, I'll explain it. Again, I'm not trying to be patronizing here. I really am not. But honest to God, for me to learn this stuff, I've got to do it in stages. I've got to do simple first and then gradually layer it on top of that. You build your foundation and then you put your other stuff on that, right? Just like what I was saying with physics. It's the foundation of everything in the universe. The laws of physics rule everything. Then we get into chemistry. They depend on physics. And then finally into biology. We'll be starting biology tonight. And chemistry. We'll be leaving the physics behind and moving to chemistry. And I admit that terrifies me. Chemistry was not my thing. I should have known in high school. I mean, it was not my thing. I'm sitting there watching all the smart kids, and I'm like, I'll get you after school, you little son of a bitch. That's what I went through. Then what do I do just to show how dumb I really am? I go to university and I sign up for science, because that's what I always wanted to do, right? When I was in grade 5, I decided I wanted to be a biologist. So I memorized the Latin names of all the major mammals and animals in British Columbia, plus the trees and that. I can still recite them. I was serious. I got all the books from the provincial museums, and I read about occipital lobes and all sorts of stuff that no human beings, when they're in grade 5, should be reading. Then I get to university. I go into the chem lab. By the way, there really are labs out there. There's people. I actually walked around in a white coat for a while until I realized that I was so dumb in chemistry. Well, what I did is I walked out of chemistry and walked down the hall to the English department, signed up for an English course, English 101. The instructor said, read Heart of Darkness. It's a novella by Joseph Conrad. So I went and read Heart of Darkness. Write an essay. Okay, so I wrote an essay. I got 90% for the essays. First essay I ever wrote at university. 90% here, dumbest kid in the class there. What am I going to do? I became an arts major. But there was always that frustrated scientist. Not a scientist, but just somebody who loves life and is really interested in nature. And I was always like super keen on animals, especially cats. Lions are still my favorite animal. Like, it's just a coincidence I was born in July. I don't believe in any of that stuff, by the way. Anyway, what we're going to do tonight is we're going to, I got just something I forgot, a couple of small things I forgot to tell you. Then we'll cover plate tectonics, because it's important. And you don't have to know it in depth, but you just have to know how it works. It's like anything, like, I don't know, respiration or photosynthesis. You can put a simple equation on the board, carbon dioxide plus water plus a few photons from the sun, wham, converted into chemical energy. Next thing you know, you got your universal food. C6H12O6, which is? Oh no, this is Ferris Bueller's Day Off, all over again. Anybody?
Carbohydrates.
Carbohydrates, specifically. Good girl. Sugar, C6H12O6. That's the universal food that everything in the world, in one way or another, depends on. Another thing is respiration. There are two main, I was going to cover this later. Well, we'll cover it later. Anyway, just pointing out that there's a couple of simple reactions that are so important that we have to know roughly how they work. There are certain molecules that are so important, proteins, lipids, carbs, and nucleic acids, that we have to know a tiny little bit about. Not a lot, just a bit. I'm going to reinforce the idea that, again, building from the simple to the complex, we started, remember, with a Big Bang, so the first things created were the most simple, quarks, electrons, so the smallest, simplest things first. Then they finally combined to atoms. Let's have a look at our trusty timeline here. So the first thing is you get nuclei at 3 minutes into the Big Bang, okay? Then you get atoms, and you get atoms at 380,000 years into the Big Bang, because before that, it was too hot for anything to get together. But at 380,000 years, it's cooled down to below 3,000 Kelvin, and it's cool enough, and there's little enough energy that atoms can get together. So electrons can finally get together with nuclei and form atoms. And then atoms get together and make molecules. Molecules get together in short chains and make monomers. Monomers get together in longer chains and make polymers, and you finally end up with your 4 essential macromolecules: proteins, lipids, carbohydrates, and nucleic acids. Nucleic acids, that's DNA and RNA. We'll go into that a bit, but again, not too much. Carbohydrates, well, C6H12O6, lipids, glycerol and fatty acids, and proteins. These are the macromolecules. These are the monomers that make them up. Proteins are made of amino acids. Lipids are made of glycerol and fatty acids. Carbohydrates are made of monomers, like disaccharides, monosaccharides, disaccharides, short chains of sugar. Yeah, I'll even tell you why saturated fatty acids are bad for you. And again, it's just because of bonds. And in chemistry, you're into bondage, and proteins, finally. Amino acids are the monomers. So we're looking at that. And let me think, what else? Well, let's finish Schrodinger. Okay, I think he's around number 30-something. Oh, wait, maybe I should follow what you and I decided we should follow. Okay,
Yeah,
let's
look
try it.
there, because I can't see that far, so
Okay,
you're going to have
so-
to read me the number if I don't find it right away, okay? But I know
It's all
where
right.
it is.
It's all right, hon.
I got it, baby.
No, wait, somewhere in here, there's that first
37.
page.
Oh, do you need help, darling?
There it is.
Yoo-hoo.
You can tell Denise wrote it. So I was freaking out because I thought this would be pretty straightforward. I mean, there's a lot of material. It's a history of life on Earth. They don't even know how many species are on Earth. I was just reading a report by Mora et al. From 2011, and they figure there's around 6.7 or 7 million species on the planet. But that report goes really low on bacteria, like prokaryotes. It only lists about 10,900 species. Most people think there's more like millions or even billions. So the total number of species on Earth is unknown, but a good guess is around 10 billion, or 10 million rather. That's way more than that have gone extinct. 99% of everything that's ever lived has gone extinct. So there are estimates that the numbers that have gone extinct are like 5 billion and up. So just about everything that ever was isn't. A tiny bit of it is preserved in the rocks. Those are called fossils. Our problem with learning about the early part of the universe, our early part of the Earth, is that everything's been recycled and there's almost nothing left of this original era. And we're going to be looking at the recycling process of this set, because that's what we started last week. We started with Wegener. Remember the guy that died in Greenland? And his body's buried under the ice, and it's moved about 2 meters. since he died. So somewhere under the ice in Greenland is Alfred Wegener, the
And
pioneer of the process that allows Earth to keep recycling its stuff, and which is our weather control system. So, what first? Big Bang Theory, yeah, I covered that. Schrodinger, okay, what's
37?
your guess is as good as mine.
I'm not guessing.
Oh, sorry, hon. I don't have, 37, yeah. Okay, now you remember Schrodinger. I just want to clear something up. We were talking about how in quantum mechanics, in the world of the real small, if you want to find out where a particle, like an electron or a photon is, then you can use the Schrodinger equation to do that. And I talked to you about the wave function, that psi, that's the thing at the end, the thing that looks like a candelabra. So that's a Greek thing, psi. And if you use that equation, you can find out where I'm most likely to be if I'm an electron somewhere between here and Kamloops. Okay? But what I wanted to stress is it's not like what it is, it's I'm everywhere at once. Now, I can't imagine what that is. I'm just telling you what I've read. But that electron is an electron cloud. It's a probability. Should we have a look maybe at the Bohr atom?
Okay, or did you want to look at the quantum field?
Okay, I'll look at a quantum field.
I'll show you the Bohr atom too if you want.
Okay, well, let's look at both.
Okay.
That sounds good.
So there's the quantum field.
Yes, that's Paul Dirac. He was the guy that came up with the idea that the basis of all reality is quantum fields. That thing called quantum foam, and these little tiny fields exist everywhere. There's no place that they're not. Everything has energy. There's no such thing as absolute zero in the universe, and everything is always in motion. That's one thing that I want to get across. So Paul Dirac came up with the idea that the basis of reality, and he got a Nobel for this, by the way, in 1931, so they must have thought it was a pretty good theory. Anyway, he came up with the idea they're quantum fields, and those bumps you see are what manifest themselves as particles. So when we talk about fundamental particles like quarks, we're talking, according to the people who subscribe to this theory, about excitations in the quantum fields that manifest themselves as particles. And that's all I'm going to say about physics, except to complete the idea that if I'm between here and Kamloops, it's an electron cloud. It's not that you don't know where I am. It's that I'm everywhere at once. I'm literally nowhere and everywhere, right? Because if I'm everywhere, I'm not really anywhere. And as soon as you use that equation of Schrodinger's to find out either how fast I'm going or where I am, then that stops the whole process. So you'll find out where I was there, but you've got to start the whole thing up again if you want to find out where I'm going to be in the next millisecond. So it's just bizarre. But I just wanted to clear that up. So with Schrodinger's cat, it's not that the cat is alive or dead, it's the cat is both. Until such time as you do the equation and find out where he is. Next. Oh, did I tell you about Schrodinger's marriage arrangements? Oh, well, he had a wife. But the thing is, he also had a mistress. And they all traveled together. Isn't that weird? Because I always think of people back in the 30s as being really conservative or stodgy or something, right? Like not hip like us. But everywhere he went with both women. And that was a problem for him to get a place to live. Because things were starting to get kind of nasty in Europe in the late 30s. Hitler took over in 33. The Nazis were in full power in the late 30s. They were taking over other places like Czechoslovakia and that. And a lot of people were freaking out because Jewish people were already starting to get beat up and persecuted and ghettoized and that. So Schrodinger was looking for a place to live. Now he's half Irish and half Austrian. So he finally went to Ireland. And because he was a personal friend of the Prime Minister, he managed to live there. But it was a dicey situation due to the fact that he had the wife and the mistress together. Anyway, that's it about that. No more about physics. The other thing I wanted to clear up is about the moon. There ain't no such thing as a dark side of the moon. Somebody who is my friend put something about the dark side of the moon last night, and I had to restrain myself with every fiber of my being not to say, there's no goddamn, I did. But there's no dark side of the moon. The moon is rotating. It rotates, makes one full revolution every 27.3 days. And that is timed so that when the moon turns, the Earth turns at such a rate, like the Earth turns every 24 hours, the moon turns every 27.3 days, in such a way that no matter what's going on, we're always seeing the same side. But that other side gets hit by as many asteroids as this side and as Earth, and it gets just as much light. There is zero difference. There's no dark side of the friggin' moon. Okay. Okay, I was just going to tell you a couple of neat things that I found out this last week because they bear directly on what we're talking about. And they are the idea that everything has changed and everything is connected, right? You just need to understand. I'm not speaking metaphysically. I'm not subscribing to any woo-woo. I mean, everything really is connected. Biologically, all over the face of the Earth, and probably everything in the universe too. But we already covered that. We talked about heat death and the end of the universe and all that. And we're not going there anymore. But anyway, I just happened to come across a little factoid that I didn't know before, and that was that coral can emit fluorescence. Now, what coral does is it soaks up light, and this goes back to what we were talking about in physics. You know how light comes in quanta, right? Yeah, and you're all going, well, yeah, it doesn't. Anyway, light comes in quanta, and when we see light, like what happens? Okay, you got your coral sitting there, nice coral reef. We should probably, oh, there, coral reef, thanks, hon. And so we got our coral, which is little animals living inside little calcium carbonate houses. And these little animals have got little symbiotic things, prokaryotes, living, by the way, we'll get to find out what prokaryotes and eukaryotes are today. Anyway, these corals have got other littler things living inside them, and these little things feed them. These little things inside the coral, they take in light. They're called zooxanthellae, which is another word for diatoms. Okay, so you get diatoms inside the coral, and these diatoms photosynthesize. That's this. That's an anabolic reaction where you take carbon dioxide and water and light and make sugar. So these little symbionts, endosymbionts, living inside the coral, they get a good deal because they get a place to live. It's nice and safe. The coral gets a good deal, because even though coral's an animal, and even though it's got little tentacles and it captures things and eats them, it also has this endosymbiont which also feeds it. So we found out that even corals are perfectly capable of feeding themselves with their little poisonous tentacles. They're called cnidarians. They got these little stingers. Even though they can do that, they prefer to get fed by their endosymbiont prokaryotic. No, I beg your pardon, the endosymbionts are eukaryotic. Anyway, they get fed by them. So they get 90% of their food from these little things living inside them. That's what corals do. As you probably know, the coral reefs all over the world are dying because the water is too warm and too acidic. So the coral are expelling those little endosymbionts that usually live inside them, which means the coral will starve to death in about 9 or 10 months. And so when the corals expel their endosymbionts, their color goes because it's the endosymbionts that have the color. And so the corals turn white. You've probably heard of it, right? Coral bleaching? You must have read about it. Well, that's what's going on. The corals, the water's too hot, and the corals are booting out their endosymbiotic, eukaryotic, little dinoflagellate helpers. And they're booting them out, and then the coral dies. Well, that's what's going on all over the world. But the cool thing I found out, that I knew all that before, right? What I didn't know is that the coral absorbs light from a higher frequency and then re-emits it at a lower frequency. And the proteins in the corals, I guess it's their epidermis, the proteins there act as a sunscreen for the coral and protect it from harmful UV radiation, which is coming down in a big way in the tropics in that shallow water. UV is one of the enemies of life. It ionizes our DNA and wrecks things, gives us stuff like cancer and all that. So it's not good for us. So that's why we had to get a magnetic field early on in our history as a planet in order for life to be able to be protected from that UV. So the coral then absorbs light through these proteins, and then it re-emits it as fluorescent light. That's what fluorescence is. You take in a light, you take in some photons at one energy level, and then you re-emit them at a lower energy level, and that's what fluorescence is. And that's where light comes from, remember? It's from electrons going to lower energy levels. So I know I just babbled a lot of phrases that I wasn't intending to, but we're going to be covering all this stuff as we go along, okay? And one thing after another will become clear. So coral uses light in a way, and the proteins that it has evolved to process that light as a form of sunscreen, as a form of protection from UV. Another cool thing I found out is that this thing in the corner of our eye is called a plica semilunaris. Now, I did not know that. And the reason that I'm interested in that is because we evolved that. Could you give a, oh, God, you're good. We evolved that about 400 million years ago when fish were evolving to become land-dwelling creatures and were turning into what we call tetrapods. Then after that, they became amphibians. Then they became amniotes. And then they became synapses and diapses. Well, we'll cover all that when we get to it. But anyway, about 400 million years ago, we developed a nictitating membrane. That's a third eyelid. Third eyelid. And some animals have still got it, and some don't. This is all we've got left of it. It's a little thing in the corner of our eye. But some other animals have got it. For instance, sharks. Now, I didn't know this until yesterday either. I mean, in a way, this is what, it's both inspiring and discouraging, right? Because, I mean, I've been doing nothing but read about this stuff now for 2 years and 3 months. Because when I walked in on Claire that day and scribbled off some of this stuff on that piece of paper, I wasn't consciously intending to do this. I thought, no, it's just an idea, right? But I think what happens is those things, remember I talked about the sliver in your mind, that movie, The Matrix? Well, I think that was a sliver in my mind. I think it started working. And I think ever since then, I kind of thought on a subconscious level, maybe I was going to be doing it. So I've been studying this stuff all the time. And I've learned a lot. But I mean, up until yesterday, I didn't even know a simple fact, like the sharks are divided into two groups. One group has an anal fin. That's the back one there. Well, here, let me draw a shark for you. This should be fun. I haven't tried to draw a shark for years. Okay. Oh, wait. Now let's make it a head or a carol tail. There we go. Put an anal fin on them. Throw a couple of pectoral fins, maybe a pelvic fin. There we go. Some gill slits. 5 of them usually. And maybe an eye, because that's what we're talking about. So, if you're a shark with an anal fin, then you have got a nictitating membrane. That means when you go to eat something, like you're coming up under some prey and you're going to eat it, you can roll your nictitating membrane across your eye and protect your eye so it doesn't get hurt by a thrashing organism. If, on the other hand, you're the other kind of shark, without an anal fin, like a white shark or a mako, 2 of the world's deadliest sharks. They're in the mackerel family, mackerel shark family. Things you find out. Anyway, these sharks have nictitating membranes, but ones without anal fins, white and makos, they have no anal fins, they have no nictitating membrane. That is why the eye of a great white was black when it's striking. If you look at video of a great white biting, you'll see its eye go black. It just rolls it's because it doesn't have a nictitating membrane, so it rolls the eye right back. That's why in Jaws, that scene in the boat when that guy played by Shaw, what was his name? Ralph Shaw? Shaw. Anyway, do you guys get out ever? Do you ever see movies? Anyway, remember when they're in the boat and it's kind of dead in the water, and I don't know, not the protagonist, but the guy played by Robert Shaw. Anyway, he's telling them about the Second World War when they got attacked by sharks, when their boat was torpedoed. and the sharks would come around picking everybody off. That's when I first heard about that. He says, because when they bite you, he said, their eyes go black. And I thought, really? So there it is. They do. Anyway, that's one thing I found out. Now get this. Peregrine falcons. They use it when they're diving. That's the world's fastest animal. It can do it 320 kilometers an hour in a dive. And they use their nictitating membrane as windshield wipers while they're doing it. But this is the coolest thing. Babies in the nest, those baby raptors, like baby hawks, baby falcons, baby eagles, they're vicious little guys, eh? And when they get big, the parents are feeding them, and the young are as big as the parents, and the young have got these little beaks in there. So they use the nictitating membrane to protect their eyes when they're feeding the young. I just thought it was great. And my final one is polar bears. They use it to not go snowblind. I was at Mount Baker once on a sunny day, and I probably went snowblind. I was bright red by the end of the day, or sunburned. I could hardly see. It was bad. And so they use their nictitating. Okay, right. Covered
Camels
that.
have them too.
Sorry?
Camels have them too.
Yes, they would. Yeah, they've got those huge eyelashes.
They have the second eyelid to protect them during sandstorms.
Exactly. The haboobs. That's what they call the sandstorm. So, there's your eye. I thought I might talk briefly about the Himalayas too. Just because we're on the interconnectedness of all things, and I got number 85. Denise has put a lot of work into these pictures. What was I going to show? Oh yeah, okay. Where are the Himalayas on that map? Well, oh wait,
You've got a pointer.
I do. Let me try to use it. Okay. Where are the Himalayas?
The Himalayas.
The Himalayas! Hunter! Support mutiny!
You're wrong way.
Wrong way. Okay, these are the Himalayas, 2,900 kilometers long. What happened was, about 100 million years ago, Madagascar and Africa were here, just more or less where they are now, and India was there. So this was India, and that was Asia, and that was Madagascar. Well, tectonics happened. India started moving, and it set a record, actually. It moved from there to there in about 50 million years, and that's about the fastest any continent has ever moved. That's really roaring. So India migrated, and it smashed into Asia. And in smashing into Asia, it created the Himalayas, the world's tallest mountains. They're so much taller than everything else, there's not even any comparison. Forget North America, forget the Rockies, forget the Andes. If you look at the 200 highest peaks in the world, 180 of them are in the Himalayas. So those are the highest mountains on Earth. And my point is, it changed the atmosphere of the whole planet. When something that high and that big goes up, what that did is it started to draw winds in from the ocean, because you know what happens, like it happens here every day. I'll be looking out toward the coast, down the valley, and you see weather coming in, or wind, and as the interior heats up, it sucks in air from the coast, and the air comes ripping up the valleys and then up the mountains, and it eventually, if enough of it gets up there, enough moisture gets up there, you're going to have some rain. So what happens is India migrates, smashes into Southeast Asia. The mountains go up. It's because they're so high. Mount Everest is, let me think, 8,848.86 meters high. That's 29,031 feet. That's a big mountain. And there's a whole bunch of others. There's another one that's nearly as tall, and a whole bunch that are over 25,000. Like I said, they're all there. So what it does is that sucks the air up. You got this warm air. The air hits the mountains. It rises, it rises, it rises. It dumps all the moisture, which is why you've got tigers and monkeys and stuff down here. And when it gets to the other side, there's no moisture left, and there's a vast desert there. And see that desert? That's the Gobi. We'll talk about camels in a second. That's where they are. Look at that. There's Africa. Look at the deserts. There's the North American deserts. You notice how they're all about the same latitude? That's because the world is turning that way, which pushes the winds that way, and the Coriolis force pushes the winds above the equator up there, and it takes the ones below the equator, it takes them down there. So we've got all these cells, these weather cells in the northern hemisphere that are going around counterclockwise, and the other ones down here in the southern hemisphere that are going around clockwise. So that's why the weather cells are doing that. I wasn't intending to talk about that, my apologies. What I was trying to get across was the idea that the Himalayas and other events like that on the surface of the Earth profoundly affect everything else. Because what happens is the Himalayas cooled the planet to the point where people thought they might have been implicated in bringing on the ice ages that happened later. Although I was just reading a paper that doubts that. But they had a profound effect on the climate, and the rise of the Himalayas is generally thought to have cooled the entire planet by several degrees. That's how things are interconnected. North and South America. Okay. There's our trusty map. I've got 128 here. Is that?
Thank you, because I can't see the
Sorry.
numbers.
Okay. Well, I don't want to turn my. Well, sorry. I don't want to turn my back on you. Okay. So yeah,
What number do you want?
128. I'm going to talk about great interchange.
Marsupials.
Yeah. Okay. So here's a couple animals we're very familiar with. On the left is the opossum, distinguished by the fact that it has more teeth than any other mammal, over 50 teeth. They're also supposed to eat a lot of ticks, so if you ever find one around here, which you won't, by all means try to preserve it. There are a few in British Columbia, but as far as I know, they're all down in the lower mainland. And they at one time were restricted to the south side of the Fraser River, according to Ian McTaggart Collins' Mammals of British Columbia, 1959, because I was reading it avidly when I was in grade 5. That's something I know. That's a kangaroo, as you probably figured. That's a great gray kangaroo, which is the world's largest marsupial. Which brings us down to my next topic, marsupials. Smooth? I thought so. Anyway, where did marsupials evolve? Most likely South America. When? About 125 million years ago, or maybe 20 million years before. So, where are we on our timeline here? Okay, now what we're talking about then is what did I say? 104, yeah, okay, let's say 125 million years ago. So in the Cretaceous. So they evolved when the dinosaurs were still around, and they made their way from South America. Now I'm going to need a map here probably, of Pangaea.
Okay, no problem.
I got 123. Oh, well,
You want a map of Pangaea?
yeah, that'll be good. Okay, so when they evolved, when marsupials evolved, here's North America, South America, Africa, Antarctica, Australia. So they evolved in South America, let's say, and then they made their way to Antarctica and Australia. Now, Antarctica in those days was warm and temperate. There were dinosaurs there. It was a perfectly nice place to live. So the marsupials started there, migrated all the way over to Australia, and then the continents broke up. And the ones that were left behind in South America did okay, but the ones in Antarctica, everything in Antarctica that was living on land went extinct because it got too cold. And that had to do with changing ocean currents and the position of the continents too. So finally, what happened was they got eliminated in Antarctica and outcompeted in most other places, but Australia split off before placental mammals, that's mammals like us, could get there. So the marsupials ended up ruling Australia. Australia has no placental mammals in it. And Antarctica obviously doesn't, because it has no permanent land-based life forms. So that's why all our marsupials are in Australia. Now what happened then, that accounts for marsupial distribution and the fact that the marsupials are in Australia and what's the one marsupial in North America? Got a lot of teeth. Good girl. Right. So that's why the only marsupial in North America, I think, is the opossum. The rest of them are in South America, but most are in Australia. Which brings us down to camels. Camels, do you know that? The camels evolved in North America?
Yeah.
Yeah. Good for you. 44 million years ago. and they spread to South America. And no, they didn't. What they did is they evolved in North America, and then about 6 to 7 million years ago, some of them moved over to Asia. And then the continents moved apart, and the camels in North America became extinct, but the ones in Asia spread out. And they started, remember we were just looking at Tibet up behind the Himalayas, the Gobi Desert, that desert area. That's where they ended up. And they ended up as two-humped. They started as two-humped camels, and then they gradually spread out, and they were domesticated as dromedaries. So the dromedaries were introduced in the Middle East about 3000 BC. Bactrian camels still exist in the Gobi Desert. They're extremely endangered. There's about 250 of them, and they're one of the world's toughest animals. It gets 40 below in the winter and 40 above in the summer. There's almost no water, and yet they survive. They are one tough animal, and that's how they got there. And they're no more, there's none in North America. But they are in South America because 3.6 billion years ago, I'm going to need a map. A map, baby.
Of what?
Anything, just the world, so I can show them North and South America joining.
Join?
I got 80 now. I got 123. Now, okay, well, you can imagine North and South America, right? 3.6 million years ago, they came together. Yeah, that map doesn't help me.
Okay.
I need a map of the world.
Okay,
as it
I
is
wasn't
now.
sure
Just
which
use your
one.
imaginations. There's North America, there's South America. 3.6 million years ago, they come together, and anything that's in South America can move north, and everything that's in North America can move south. So that's the great American interchange, and it occurs as a result of North America and South America joining. So many marsupials went north, but they all became extinct except for the opossum. A lot of them stayed down here, and they're still doing all right. They're called the marsupials are still down there, and the camels that are down there are called llamas and alpacas and those things. Those are camels. If you just look at the face of one of those, you'll see it's clearly a camel. Tough creatures, tough creatures. I got a lot of respect for them. So anyway, due to the fact that those two continents joined, we got a completely different diversity of animal species in both North and South America. And, it also changed the climate. Here's Europe. And let's see. Maybe this would be a good time. I think this might be a good time to follow the schedule that I was going to. Just let me see where we are. Okay, no, I'll just carry on in this. So what it did was, once that closed, it completely changed the ocean currents. They used to flow through there. But once they couldn't, the ocean currents were redirected, and one called the Gulf Stream, you've probably heard of it, the Gulf Stream developed, and it carries warm water, all the way up here to near the Arctic, and then it sinks, and then it comes back down as cold water. Warm water rises, goes way up here, sinks, comes back down. So that's the North Atlantic meridional overturning. It's got a really fancy name. What it does is it stops Europe from going into an ice age. If that current were not transporting heat from the tropics up into the higher latitudes, Europe would be 10 degrees colder. That's Celsius, and that would put it right into an ice age right now. So we want to make sure that doesn't slow down. The last time it slowed down or failed was around 11 or 12,000 years ago. There was ice all over North America, and the ice melted. That's what got us into our current period called the Holocene. When the ice melted, a whole pile of fresh water, they're not sure by what route, and this is just a theory, by the way, flowed into the Atlantic Ocean and made it a lot fresher. And so that amount of fresh, cold water shut that current down, and it plunged Northern Europe, especially, and other places in the world, into a thing that they call the Little Ice Age. It's actually called the Younger Dryas event, and it happened about 11 or 12,000 years ago. Dryas is a type of flora. Okay, so my point then is that if you change something on the surface of the Earth, And those changes on the surface of the earth are governed by changes inside the earth. If you have to consider that what goes on inside is going to change what is going on outside. That's all I'm trying to illustrate. By looking at both the animals and the climate, I'm just trying to show you that everything is connected. Oh, here's another neat thing. Remember I mentioned diatoms a little while ago? They're little tiny, they're unicellular creatures that would be animals, except that they've only got one cell. So they're in that kind of awkward group that we used to call protists, and which I think is not an official taxonomic term anymore, but I still really like it because it's a good way to describe those organisms that don't fit anywhere else. So we've got diatoms inside, we've got diatoms, okay? They produce 20 to 50% of all the oxygen in the world. They're little one-celled organisms that live in the water, and they have glass houses. They literally live in glass houses. They've got these, yeah, look at that. Isn't that beautiful? These are just a few of them. They're just wonderful. These are made of silicon dioxide. It's the same stuff that opals are made out of. Opals are just silicon dioxide that's hydrated. So basically, this is sand, rock. That's what they're living in. They're glass houses. And they capture prey, and in some cases, they can make their own food, too. So we've got diatoms in the ocean. Now I'm going to need a map, please. 124? No?
I don't think that's a map.
Tell you what I could do. I could declare a break. It's
Yes.
past 7:30. Want to do that? Take
Yes.
a break for a couple of minutes?
Yes.
Let's do that. I hate to do it, but I guess we should
Yeah, go on.
kind of get back together if I'm going to finish this.
Yeah, carry on, dear. You're doing perfectly. This is awesome.
Okay, everybody.
Enjoy the rest of your time. No, that's fine.
Shush.
Well,
Shush.
Teacher voice.
other
try
teachers
this
would
one
go
more
out
time.
and they would say nicely, okay, everybody, let's be quiet now. I just got tired of that, you know. It's just easier to say, shut up! You know, it works.
He had a reputation at school, that's for sure.
Learning is important. That's what school's for. You're going to be at school, be in your class, not in your bloody locker. Don't be outside of my room. Okay, I was going to make a point with the diatoms. And the reason I wanted a map is so that we could see Africa and North America. Maybe we're not ready to start yet then.
No, we're good. We're good.
Okay, well, I'll wait a second. Okay. I find that the challenge in this is that everything is connected. That is what has been screwing me up. In trying to present it, the easy thing and the sensible thing is to take it strictly in chronological order or some kind of straightforward order. When we were doing Alexander, he only lived from 356 to 332, so it's just a matter of first he did this, then he did this, then he did this, then he went there, blah, blah, blah. With this, every time I go to talk about something, I think of something else that's connected to it, and that is what's making it so hard for me to keep my brain focused on a certain track here. I find it very frustrating because as a teacher, above all, I want to be clear. That's the most important thing. That's why I'm always trying to clarify these things. Anyway, with the diatoms, they live in the ocean. They photosynthesize. They produce 20 to 50% of all the oxygen on the face of the earth. They're extremely important little devils. They live in glass houses. Those glass houses are really useful for other things. So let me show you now.
You want to go back to the map?
Yes, I want the map, please.
Okay.
Okay. The diatoms live in the ocean. Here's Africa. Way up there, see how deserty it is? That's the Sahara Desert, the world's largest desert. Okay, up in the middle of that desert is a place called Ancestral Lake Chad, prehistoric Lake Chad. It was once a lake about the size of Lake Ontario. It's below sea level. It dried up several thousand years ago because due to a warming climate, the North Africa, which had been a fertile area in the days of the Roman Empire dried up and became a desert. And Lake Chad evaporated and is now a vast dried up lake. Now, Lake Chad was full of diatoms, little creatures that photosynthesize in the ocean. It was full of diatoms. Now, for 100 days a year in that area around Lake Chad, which is called, by the way, in case you want to look it up, it's called the Bodele Depression, Bodele, if you want to look it up. So what happens is about 100 days a year, strong winds come up. And those winds pick up the dust from Lake Chad, dried up Lake Chad, and they blow it across the ocean. And where does it land? It lands right there, right where the world's biggest rainforest is, the Amazon rainforest. How much? 27 billion tons of diatoms get carried. No, wait, 27 million tons. Sorry, don't want to make that mistake again. 27 million tons of diatom dust, diatomaceous stuff, gets carried across the ocean and fertilizes the Amazon rainforest. And that's how the Amazon rainforest gets fertilized every year. Last thing I want to talk about is otters. Number 97.
Thank you, dear.
I already knew this. I didn't just discover it in the last week, but it's cool. California. We don't need a map. You know where California is. Northern California. There used to be a population of sea otters that ran all the way from Alaska and the Bering Sea, right down British Columbia, right down through California. The last sea otter in British Columbia was shot in 1929. The sea otters worldwide were almost exterminated, as I'm sure you know, because they have the most valuable fur in the world. And the reason they have the most valuable fur in the world is because they're the world's smallest marine mammal. They're the world's largest members of the muscelids, which are the weasel tribe. So these otters are the world's biggest weasels, but they're the world's smallest sea mammals, and they have no blubber. All other sea animals that I can think of, anything from manatees to seals to walruses to stellar sea lions or whatever, they all have blubber, whales, the whole bit. Not these little sea otters. So these guys have to rely on their fur, and their fur has anywhere from 100,000 to nearly 1 million hairs per square inch. It's the densest fur in the world, and that's why they were hunted almost to extinction. All the sea otters in BC were exterminated, and all of the ones in California, except for a few small pockets that nobody knew were still alive. Well, they finally passed some laws saying it's now illegal to exterminate sea otters, and gradually the populations have been returning. So what happened down in California was they had an invasion of green crabs. These green crabs came in from another part of the world on the bottom of boats or in the bilge water like they usually do. And they infested this area of Northern California, and they were destroying the local fisheries. And then the sea otters show up. They love green crabs. And they have decimated the green crab population, restored the eelgrass ecosystems that are so valuable, and saved the fisheries. Sea otters, ladies and gentlemen, and Hydra lutris, the world's smallest sea mammal. So I just wanted to kind of show you how everything's connected. Now let's look at plate tectonics. We're going to need I've got a whole bunch of them. What about 88? 68, we'll start with him. We'll look at Wegener and then at John Tuzel Wilson. So we know that guy. He's the guy that came up with the theory of plate tectonics. Why didn't anybody believe it? Well, he said at one time all the continents were stuck together, but they drifted apart. And he said they drifted apart, and now they're here and there and everywhere, but they originally were together. And other people said, yeah, okay, it looks like they were once together, but how did they move? Nobody came up with an idea. Okay, now I remember back in the 1950s, we got our first TV set in 1957. 1958, I used to watch Walt Disney, like Davy Crockett and stuff like that, right? But Walt Disney also used to put on scientific programs, and they had one on the International Geophysical Year. I can remember 1958. And they had pictures of them out there drilling down into the bottom of the ocean. And so, as a result of that activity, they were able to realize that plate tectonics was a real thing and to start understanding the mechanisms by which it worked. And a Canadian named John Tuzo Wilson was the guy who came up with a mechanism to explain. Okay, Wilson said, okay, in the first place, he said, there are about 13 or 15 major plates on major continental plates. And they sit on the very top of the Earth. And let's see, before I explain that, I got to see the cutaway Earth. The cutaway Earth.
Cross-section?
I don't know which one it is, hon. I want to show you a cutaway of the Earth so we can look at the different layers and look and see how this happens.
Okay.
Sorry.
Don't you have the number there?
Well, I got 88.
88 it is.
I got 82 and 81 and
88,
83.
baby.
That's it.
88. Honey, 88.
Look at the
Look
map.
behind you.
Right. So there's a cutaway of the interior of the Earth that should explain it. We can see that in the interior, the very bottom, there's a core. I mean, what happened was when Earth formed, obviously it cooled from the outside in, and the outside formed first. All the lightest stuff is on the outside, heavier stuff as you go down, until you've got all iron and nickel in the middle. In the middle, it's so hot that it can't be liquid. There's too much pressure down in the center of the Earth for it to be a liquid, so it holds it in a solid state. And the average temperature in the core is about 5,500 degrees, which is the same as on the surface of the sun. The hottest part of the Earth is where the inner core, which is solid, and the outer core meet. I remember I mentioned a phase transition in the first lecture and how phase transitions create energy. Well, you've got a transition there at 2,900 kilometers between. I'm going to see if I can use this thing again, because it is handy. Just a sec. So, down here is the core. That's the core right there. That's the mantle. And that is the crust, and that is the asthenosphere. Now, asthenosphere comes from a Greek word meaning weak, because this is not a strong part of the crust. Because this is a weak part of the crust, what's on top of it slides over it. What's on top of it is thicker and harder. This is the oceanic crust, and this is the continental crust. They're made out of two different things. The oceanic crust is made out of basalt. I talked about that before. That's that dark, dense, heavy volcanic rock. And the continental crust is made mostly out of granite. That's a lighter rock. And it has lighter elements in it. Let's take a look at 40. I think that's the periodic table.
Is full periodic?
Yeah, this 42, man. Anyway, the lighter elements here are what make up the surface of the Earth. So, what are rocks? Okay, here's a crash course of rocks. If it's... Okay. All right, I'll write it before. Mafic.
Do you want a picture of the mafic and felsic?
Oh, sure, yeah. So the light stuff's on the top, the heaviest stuff's in the middle. Okay, that's a mafic rock, and a felsic rock. Felsic, mafic. Felsic stands for feldspar and silicon. And mafic stands for magnesium and iron, because the Latin word for iron is ferrum. Okay, now back to the previous slide, please, of the cutaway. So there's two rocks. There's that's actually a piece of metamorphized schist, and so is that. They're called gneiss, G-N-E-I-S-S. Well, anyway, if you ever hear of a rock that they call gneiss or gneiss, it's G-N-E-I-S-S, and it's a very old type of rock, and constitutes probably some of the oldest rock we'll find on the face of the Earth. So, the felsic stuff is on the top. The mafic stuff is buried down deeper. The felsic has got a lot of light elements in it, like aluminum and silicon, and the mafic has got heavier elements in it, like iron and magnesium. How's that? Crash course in rocks. The other thing you have to know, igneous, volcanic, means coming from fire, right? Remember that from school, igneous? 2, sedimentary. When the igneous rock finally breaks down into little grains, those grains form mud or sand, and those become sedimentary rocks. Third kind is metamorphic. Now, this is at the heart of the Malanka, or of the site of the plate tectonics. The idea that everything is recycled, because what starts out in the top ends up going down and then coming back out at the top again. What Wilson did was Wilson said, okay, the surface of the Earth is made out of 15 plates. These plates float on top of the asthenosphere there, which is weak. When these plates come together, one goes under the other. That's called subduction. So when the two plates come together, we have a picture that actually, well, you got your oceanic crust, you've got your continental crust. The oceanic crust is thin, the continental crust is thick. This is, I don't know, average of around, say, 50K thick. This is an average of about 10K thick. When this, which is dense, meets this, which is less dense, this goes under that, right into where the fish are in the ocean. And as it goes down, eventually it gets deep enough that it hits an area where it starts to melt. Because what it does is it carries water down with it. And the water acts as a flux. So when it gets down to a certain depth, which is about 660 kilometers, you get melting. And what that does is it allows magma, which is melted rock under the ground, to make its way up to the top. And it comes out as volcanoes. So that's how it works. The oceanic plate gets sucked under the continental plate because it's heavier. It dives down, takes water with it. The water gets down to a certain depth. The water acts as a flux. Stuff melts. The rocks down there melt. By the way, are you guys familiar with a gem? Is there a gem called peridot?
Peridot.
Yeah.
Oh, okay. Well, what that actually is, it's a rock called olivine, which is magnesium, which is a combination of magnesium, silicon, and oxygen. Your basic rock, and that's probably the most common rock on the face of the Earth. There's probably more of that than anything else. And when that olivine or magnesium silicate melts, it comes up to the top, comes out as volcanoes, and what the volcanoes do is they spew ash and CO2, carbon dioxide, into the world, or into the atmosphere. So you've got subduction, and it's carrying all the minerals here down underneath into the mantle, which eventually is going to be recycled as volcanic material. So the rocks get recycled that way, but it's not the only thing that gets recycled, because there's this thing called CO2. And CO2, let's look at our electromagnetic spectrum. I think that's number 20.
You got it.
Thanks to James Clerk Maxwell, we know there's an electromagnetic spectrum, and we know that it's got various different wavelengths in it. God, how was I going to connect? Huh.
CO2.
I was going to talk about recycling CO2, but anyway, I can't remember what kind of connection I was going to make with wavelength. Anyway, don't worry about it. CO2 is in the atmosphere. It's expelled by us, animals, as we respire, as we breathe. What happens is, when it rains, the CO2 in the atmosphere gets turned into carbonic acid by mixing with water. That carbonic acid gets into the rivers and the lakes, and it gets washed down into the ocean, and then the carbon in the carbonic acid gets buried in the bottom of the ocean, which is really cool, literally, because if that didn't happen, it would keep building up in the atmosphere. And now I remember, because that's how it works, is CO2 traps heat in the infrared. That's what it does. CO2 is only 0.04% of the atmosphere. It's almost nothing. But that tiny little bit traps so much heat in the infrared that very much of it builds up in the atmosphere. The world's temperature goes up. So plate tectonics not only recycles all the minerals in the world, but it also recycles CO2. It takes CO2 out of the atmosphere, locks it in the rocks, takes it to the ocean, puts it in the bottom of the ocean, subducts it way down into the mantle, and then it all comes back up as volcanoes. And that's how the planet has been regulating its temperature ever since the plate tectonics. Plate tectonics is what makes the planet habitable. Planets that don't have plate tectonics, like Venus, also have no oceans, no magnetic fields. You know how hot Venus is? Venus is 464 degrees Celsius. You know how much heat you've got to have to melt lead? 327 degrees. So lead would be melting and running around in rivers on Venus, and that's because Venus has a CO2 atmosphere. It's 97% carbon dioxide. So next time you look at Venus, think about that. What's that, hon?
That is a shot that NASA did where they looked through the exterior to see what the actual planet would look like underneath.
Was this the sun?
No, it's Venus.
That's
what,
Venus?
Yeah,
Wow.
that's it in real color, like it's real color.
Yeah.
That is it through NASA surveying to see what it looks like underneath the white, the cloud. Yeah.
So that's probably more or less like we're going to try to cover early Earth, right? And I was hoping to get into it tonight. And that's probably the color it was. Because
Yeah.
on early Earth, there was no oxygen. There was no oxygen up until 2.5 billion years ago. So the first 2 billion years of Earth's history, zero oxygen in the atmosphere. There was tons of oxygen, but it was all locked up in the rocks, right? We just saw. See that? MgSiO4. See that big O there? This is the biggest constituent of rocks, is oxygen. We always think of it as a gas, right? But it gets locked up with other things because it loves to hoover up other people's electrons. Oxygen is roaming the universe, looking for little Red Riding Hoods with little baskets full of electrons. Come here, little girl. You know, so oxygen is a big electron acceptor, and wherever there's oxygen, you're going to find it reacting with other elements, other atoms. And that's why up until we had oxygen-producing life on Earth, there was no oxygen in Earth's atmosphere. So the ancient Earth was a totally different place. It was the same size, same place, everything else was different. The oceans were different, the atmosphere was different, the surface of the Earth was different, the mantle was different, everything was different. It might as well have been a planet in another, universe, or not a universe, but another galaxy or something like that.
There's the
That's what?
that's the Earth.
Oh yeah, that's a picture of what the Earth probably looked like about 4 billion years ago. The ocean would have been a horrible kind of lurid green color. You know that green color when say you're going into Calling Lake or something, you pass where that mine area up there where they have these lakes, and where they put tailings. You've seen those tailings lakes?
Yeah.
Have you seen the color of green that is? It's a really weird looking green, isn't it? It doesn't look like quite a natural green. Well, world's first oceans were probably kind of a green, because they were full of iron, dissolved iron, which made it green. When life finally came along, it changed all that. The whole planet went like Mars. It turned red for a while. But we don't get to that until, get to it as soon as I can. Anyhow, so I'm trying to get everybody to see that everything's connected. Whoops. Oh, damn. Sorry, Claire. Just kicked over a coffee. Rocks are not only mafic and felsic, but also they're sedimentary or igneous or metamorphic. And the whole thing about plate tectonics, can I just go back to our plate tectonics slide,
The subduction one?
I don't know, 88 or 82 or one of those. Yeah, that'll do just fine. So thanks to plate tectonics then, we've got a habitable planet that never gets too hot or too cold. Here's a timeline of stuff we'll be looking at. So tonight we're in this area, right up here, 5.4 to 4.01. Next day, we'll get to the Archean and the Proterozoic. The Proterozoic, I won't be able to, you're going to love it, because it's got an area in it called the Boredomylion, during which nothing much happened, so we can probably skip through that fairly quickly. And then we'll be into the Ediacaran when we really start to see some life. But in the early days, it's all invisible. It's called what is called phanerozoic. Oh no, that's visible life. This is invisible life we're looking at here. So, yeah, we've done our rocks, igneous. Oh, yeah. There's a mnemonic. Can you guys? This says hoc nisibus. It's just a little mnemonic I made for myself to help me remember stuff. It stands for hydrogen, helium, oxygen, carbon, nitrogen, iron, silicon, magnesium, sulfur, and phosphorus. Everything on the Earth, basically, that's alive. These are the most common elements in the universe. Hydrogen, if you counted the total number of molecules, or total number of atoms in the universe, about 90% of it would be hydrogen. If you go by volume, about 75% hydrogen. So by volume, everything in the universe is hydrogen, 75% hydrogen, 74% hydrogen, 25% helium, and 1 point something of all the rest. Isn't that amazing? And remember, these twos were all made at that precise point 380,000 years after the Big Bang. In a very short space of time, all that was made. Everything else was made later. But all those other things, when we come down to Earth, the most common ones, in the crust, oh, I thought I was going to point to
Oh,
the crust
sorry,
of the Earth.
I'll go back.
Anyway, that didn't work out. But anyway, this stands for oxygen, silicon, aluminum, iron, calcium, and sulfur. And those are the 1, 2, 3, 4, 5, 6. Those are the 6 elements that make up the crust. So everything in the universe is made mostly of this, and everything on the surface of the Earth is made out of that.
Including
There's
us.
118 elements in the periodic table, but only a very few of them are used very much.
Do you want the periodic table?
Yeah, let's have a look at the periodic table for a sec. Out of all those elements, only a few, carbon, nitrogen, oxygen, sodium, magnesium, potassium, and calcium, those 4 over there, they make up most rocks. And so these make up, rocks are made up of that, and that. That's basically most of your rocks. Silicon, oxygen, bit of sulfur, aluminum, and your not your rare earth elements, but your alkaline earth elements over here. So all the rest, I mean, they have their uses, but most of it, no. I mean, how often do you use osmium or something like that, or rhenium or osmium? If somebody ever says to you, okay, we'll know if somebody comes from another galaxy because they'll be in a rocket ship where they'll have elements that we've never heard of before, right? They'll have new stuff. They'll be made out of different things, or their technology will be made out of different things, but that's rubbish. That's nonsense. Everything in the universe is made out of this. Everything that exists in the universe is right on that table, right there. And the vast majority of it is that area right there. I mean, really, I don't even know what some of these are. Remember I told you about the dark side of the moon? Come on, folks, there's no such thing as the dark side of the moon. You're supposed to get hit. Anyway, the far side of the moon has got, I mentioned creep, potassium, rare earth elements. These are the rare earth elements. There's your potassium over there. So creep, the near side of the moon, the side of the moon we see, the dark areas that we look up at night, that area is made out of that and these and some phosphorus, which should be right there. That's creep, K-R-E-E-P. And that's the radioactive, warmer, thinner side of the moon. The other side, again, is made out of stuff like, the other side is made out of, precisely, it's made out of calcium, silicon, and oxygen. It's called the north side. There you go. So, that clear enough? We're made out of the same stuff. Everything's connected.
Yeah.
Everything's moving. Now, I already told you we're doing 1,073 kilometers an hour, right? Because we're standing right here. Whereas if you were standing in the North Pole, you wouldn't be moving at all. You'd hardly be turning, right? takes 24 hours. So if you're standing on the North Pole, your heels basically aren't even moving. But if you're down on the equator, you're doing 1,760 kilometers an hour, something like that. So it's a big difference. But anyway, my point is nothing is still. Think of something, anything that you think is not moving, and I guarantee you it's moving. Because nothing can't move. It's impossible for things to be still if the temperature is above absolute zero. And the only place in the universe that it's absolute zero hasn't been found. The coldest place they've ever found is only minus 270.15 degrees Kelvin. And that's a couple of degrees above absolute zero.
If you're standing at the North Pole, you're still moving because you're going around the sun.
You're going around, but just think about it. The bigger the circle gets, the faster it goes. Anyway, I've got to keep going. Sorry, so I can't deviate on that. So I'm getting across the idea that everything is made out of the same stuff. And that if somebody says, yo, well, they'll have something that isn't on there, well, they won't.
Yeah.
As far as we know, that's it. Now, they can make, probably, these down here are all artificially made because they only last a few milliseconds. Like you make one of these elements down here, and they're so unstable, they literally have half-lives of thousands of seconds. So how are you going to make a spaceship out of something like that? Come on. We know what the universe is made of because you can take a telescope, hook a spectrograph up to it, point it at any star, and tell by looking at the dark lines and the colors and the patterns what that thing is made out of. So there's no excuse. We know what the universe is made of, and we know that the same four forces, gravity, the strong force, the weak force, and electromagnetism, operate throughout. We don't have a clue what dark energy is, and we hardly have any clue what dark matter is. And they constitute 95% of the universe. Everything I've been talking about, all the matter, stars, galaxies, blue whales, bacteria, people, everything, it's 5%, less actually than 5%. Kind of weird, eh? But anyway, we didn't even know that up until a few years ago. So we've learned a lot. All right, now we'll look at what is life. I think that's what we're going to do. Is that what we're going to do next?
Yes, what is life?
Okay, what is life?
All you gotta do is
I
find
think
it.
I've got to go back, right?
Yeah, you gotta
Yeah.
find it, darling.
I'll find it.
What is life?
Huh?
What is life? We're gonna do philosophy now, right?
No, it's not philosophy, it's science. Okay. Well, NASA is the big authority in what is life because they're spending more money than any other organization on the surface of the earth searching for it. So, what is life? Well, there's 123 different definitions. Yeah, we're going to show two birds here, aren't we?
Yes.
Let's do it. Let's do
Okay.
it. Let's flash them some two birds.
Okay.
Okay, so in 1969, remember telling you this last week, July of 1969, they put the first man on the moon, right? And that's when they started to discover all that stuff that I was telling you about the moon. So one thing they did to expand our knowledge of the universe is to go out into it. The other thing they did, right exactly at the same time in the 1970s, was they went down into the ocean to explore the bottom of the ocean because less was known about the bottom of the ocean than was known about the moon in those days, literally. So scientists, I think of the Woods Hole. Anyway, scientists were dragging around these detectors behind boats looking for heat signatures coming up from the bottom of the ocean. And they discovered one off the Galapagos Islands. If you picture the Galapagos, you got North America, South America. Then off the west coast of South America, 1,000 kilometers, is the Galapagos Islands. John Tuzo Wilson, the guy who came up with the idea of explaining tectonic plates, explained the process by which islands like the Galapagos and the Hawaii Islands are formed. Deep down at the center of the Earth are these things called mantle plumes. They're hot areas, and these mantle plumes go from the center of the Earth up through the mantle and manifest themselves on the surface as volcanoes. So you've got a mantle plume, Now, I'm gonna need a picture to do this, so. Which one, what number, I need a cutaway of the earth.
Okay.
Cutaway of the earth.
I'm gonna guess here.
Good. So, down, shoot. Okay, this is the mantle. Remember, we know that stuff gets subducted down into the mantle. Okay, down here, at the base of the mantle, it's pretty hot. It's about 3,700, 4,000 degrees right there. So down at the base of the mantle, there are these things called mantle plumes, and they at very hot areas that rise up. Now, what's happening is the plates are moving over the surface of the earth, right? Plates are moving, and you got a mantle plate, a mantle plume. So when something like the Galapagos or like what happens is the mantle plume goes up, it forms a volcano, and the volcano bursts through the ocean, and you get an island. That's how you got the Hawaiian Islands. Remember I told you India migrated from South America over to Asia, or from South Africa over to Asia? Well, on its way, it passed an island which we now call Reunion, which was a hot spot. So as the plate passed over the hot spot, a bunch of volcanoes came up and made the island. That's what happened with Hawaii. There's a mantle plume. You got the plate moves over the mantle plume. When the plate is right above the mantle plume, wham, you get a volcano. Then the plate moves, and you get another volcano behind that. That's another island. Then you get another volcano. And if you look at the Hawaiian Islands, they're a chain, and they all formed one after the other as the plate moved over the mantle plume. That's how the Galapagos formed. The oldest Galapagos is about 4.5 million years old, and the youngest one's only about 500,000. So it's still happening. So that's plate tectonics. And again, what plate tectonics do is they recycle everything. They keep the planet at the same temperature. Oh, here's one other cool thing. Right there, a few years ago, very recently, they discovered two gigantic things down there. They discovered it. Nobody's ever been down there. I mean, this is 2,900 kilometers from there to there. Oh, I forgot to tell you. That area, I was sitting here looking at this one day, and I looked at that and I thought, there's the center of the earth, and it's 6,371 kilometers from there to there. And I thought, 3,671. So I subtracted 2,900 from 6,371, and I came out with a figure of about 3,471 kilometers, and that is exactly the diameter of the moon. In other words, the center of the earth is exactly within, I'm not kidding you, within 10 kilometers. It's the same size as the moon. It's like we've got a mini moon in the middle of the earth. And this mini moon is the same temperature as the sun. Right there is a thing called the Bullen discontinuity, and that's over 6,000 degrees there. That's the hottest place on Earth, in Earth. 6,000 degrees right there. It's up here is around 5, this down here is around 55. But that, where the liquid meets the solid, there's an energy release, and that's the hottest part of the Earth. Anyway, so they found these two gigantic structures down there because they fire seismic waves through the Earth, doing research on earthquakes as a way of trying to figure out how to forecast earthquakes. They fire these seismic waves through the Earth, and the waves travel at a different speed when they hit things that are made out of different things or at different temperatures. So there's these two giant anomalies down there. I mean, they're huge, like 1,000 kilometers high and like thousands of kilometers across. They're these giant blobs of stuff lying down there on top of the mantle. And get this, they named them Jason and Tuzo.
Oh, great.
And Tuzo's after John Tuzo Wilson, the great Canadian geologist who discovered the means by which the planet keeps itself a nice temperature.
Wow.
So now, where did those come from? Well, some people think they fell off the bottom of the crust when it was subducted. Some people think they're left over from the days of the really early Earth, like about the time it got hit by the moon when it was all molten. Or this one, I love this one. It might not be right, okay, but I can't help it. You remember when Theia hit the Earth, the Mars-sized object hit the Earth and created the moon, right?
Yeah.
Theia plowed into the Earth. Theia's the size of Mars, which is in volume 1/6 the size of the Earth. So it plows in to Earth, gets destroyed, most of it, and the iron that Theia was packing in its core ended up in the Earth's core, which is why we've got such a big core on the Earth. Oh, well, trust me, it's a big core. And why the moon has almost no iron. It's got an iron core, but it's very small. So we've got the iron that would have been in the moon otherwise. We've got the iron that Theia brought with it. And what some people think is that when Theia crashed into the Earth, some of it sunk down to the mantle core boundary, and that those great big chunks that are lying down there today are pieces of Theia when it hit Earth 4.51 billion years ago. Wouldn't that be cool? If those anomalous structures down there were left over from that? So that's one of the theories about why they're there. Jason and Tuzo. Okay, I've told you. I wanted to tell you. All right, what is life? Well, it's that which preserves and furthers or reinforces its existence in the given environment. That's boring. Let's look at two worms. Can we look at two worms for a second?
You betcha.
That'd be number 75. So, as I was saying, they were exploring the moon, but at the same time they were exploring the ocean. Sorry, I got slightly off, but I'm back. They were exploring the ocean, and they figured that down there on the bottom of the ocean near the Galapagos Islands was a hot spot. So they sent a machine down called Alvin to check it out. We got a picture of Alvin, I'm pretty sure.
Yes.
Alvin, 74, there he is. Isn't that cute? So they sent this thing down with a few people on board, but no biologists, because they didn't expect to find any life. Because where they were heading for was 2,750 meters down. That's really deep. What did it look like? Like this. It was pitch black.
Wow.
There's about 270 Earth's atmosphere of pressure on you if you're down there. Now, the only way I can figure this is by telling you a story, and then I think we're almost out of time. I didn't realize it was getting this late. Sorry. Anyway, I used to be a scuba diver. When I was 16, I subscribed to Skin Diver magazine. There was a story in it. This guy was filling his tank, his scuba tank, right? Now, a scuba tank is 70.3 cubic inches of air, pressurized up to 2,250 pounds per square inch. While the tank was being filled, there was an accident, and the valve at the top of the scuba tank got broken off. So here's your scuba tank, right? 70.2 cubic feet of air at 2,250 pounds. You got a valve up here. You put your regulator on it, stick the regulator in your mouth and breathe. Well, this broke, and this thing turned into a rocket. It went clear through the wall of the building, 6 blocks through the air, and lodged in a cement wall. That's the kind of, and that's only 2,250 pounds per square inch. The pressure down where those things are is about 3,700 something. So I can't imagine. That's what life is living under, and that's what they found. So let's look at the two birds.
Okay. Do you want to look at the smokers?
Sure, well, okay. Actually, we're over time. I should probably take this up next week, but my point is that NASA went down, they discovered on the bottom of the ocean where nobody expected it, that there was all this life, and this life is living. There is oxygen down there, but not much. The water's 2 degrees. The oxygen level is a few percent, very little, but there is a bit, but not much. But my point is that life is living very much as it was on Earth probably 3 to 4 billion years ago, under the same kind of conditions. That had no oxygen and nothing down there. Like these worms get up to 9 feet long. And they grow really quickly. Like in 18 months, one of these things can grow a couple of feet. They're one of the fastest growing animals on the face of the planet. And they're living under these kind of conditions. I mean, nothing is doing any photosynthesis down there because there's no light. So it's a completely alien environment.
Tell
And
it.
the last thing I'm going to mention is in regard to tube worms, because we should stop. So in regard to tube worms, those over on the left-hand side are a little organism that was discovered in Australia about 11 years ago by an American paleontologist named Mary Drosser, who I kind of like because she named that one organism Obamas, after Barack Obama. Yeah, a little Ediacara organism. But these might have been some of the first worms. This is called an Ediacara, an Icaria wurriata.
Yeah.
Icaria wurriata.
Yeah.
It's from an Aboriginal word that means meeting place. And this is the kind of life that's down on the bottom of the ocean. And this is more like the kind of life that was on Earth at the beginning. And I'll be talking about life, early conditions on Earth, and the first life on Earth next week. But I got one question to ask you before I go. Does anybody know about the fact that NASA has been active in this area for from about 2001 to about 2014? NASA. Do you?
What are they
The
looking?
lake up there.
Go ahead.
You!
What'd he say?
Go ahead. Say.
It's the lake up
Yes.
up by Hat Creek with the microbiome.
Pavilion.
Pavilion, yeah.
Yes.
Lake.
I'll tell you about that. Pavilion Lake, center of activity for NASA, because it's unique among the world's lakes insofar as while the environment is not particularly hostile. Should we just show them a stromatolite before we go, and then we'll...
Okay, I'll just have to
and
look
then
for one.
We'll take it up from here next week. But yeah, Pavilion Lake, it was discovered some years ago. There's these things in Pavilion Lake called microbiolites or stromatolites, and they're made by bacteria, specifically cyanobacteria and some other species of bacteria that they think were some of the earliest forms of life on Earth. So they did a lot of research up there, both with divers, and then they brought in submersibles zooming around all over the lake. They're there for years. And that's what they saw. Isn't that cool? Look at that. Can you believe that? Pavilion Lake. Yeah, those things are found almost nowhere else in the world. There's a whole bunch of them in Australia in really salient environments and that, but other lakes in the world, you can count them on one hand, and they don't have... Some of those things are 10 feet tall and about 15 or 20 feet across at the base. They're huge. And they're down like at 150 feet of water, some of them. So anyway, I just thought I'd tell you that. I'm going to call it quits, folks.
What is NASA's interest in
Why
them?
is NASA so interested in this?
Sorry?
Why is NASA so interested?
Search for life.
Because they're searching for life
Searching
elsewhere
for
in
life.
the universe.
Okay,
And
this
Pavilion
is
Lake gives us a
connected.
mirror into what life might have been way back then.
Fair enough.
That's why.
All right.
Okay, well, thanks very much, folks. We'll see you next week. I hope. Thanks a lot.